All right, let's get started. Good afternoon, everybody. Welcome. So today, I'm pleased to welcome our second speaker of the semester. It's Abdul Zalloum of Queen's University in Canada. So before handing the microphone to him, let me mention that the recording of the first talk by Yuri Gurevich is already posted YouTube recording, so a link to it is posted at the webpage of our seminar, so you can watch it there. And I'll post the recording of today's seminar later on, hopefully this evening. So as usual, when the talk starts, I'd like to ask everybody except the speaker to mute yourself. And if you want to ask a question during the talk, then unmute yourself and ask a question. So once the talk is over and we stop the recording, you don't have to disappear right away. We'll still try to have at least a short extended period of informal discussion for those who want to hang around. And with that said, so I'm pleased to introduce our speaker, Abdul Zalloum, and he's going to tell us something about regularity of Morse geodesics and growth of stable subgroups.
Okay, thanks, Celia, for the introduction, and thank you for inviting me. And thanks, everyone, for coming. So let's start. So what's a regular language? It's going to take me a couple of minutes to define it, but I will informally tell you what it is. So a regular language is an infinite subset of words which can be produced by a finite graph. So for example, if I give you, let's say I give you the following set, which looks like L equals A, comma A squared, comma A cubed, and you keep going. Now this is an infinite set of words. However, it can be produced by a finite graph. So there is a finite graph whose labels read precisely everything that's in L. And that's exactly what a regular language is. It's an infinite set which can be produced by a finite graph. So this should already tell you that the regular language should enjoy some local to global properties, because it's an infinite subset, so that's where the globality comes from, which is produced by a finite graph. Okay? So let's do things more formally. So let's start with a directed labeled graph, not necessarily finite. So let gamma be any directed labeled graph, and let O be a unique distinguished vertex of gamma. The collection of words which can be read as labels of directed paths starting at O and landing at some vertex is called the accepted language of gamma. So you have some graph, you have some directed labeled graph with a unique distinguished vertex. And the accepted language of this is precisely anything that you can read starting at that unique distinguished vertex and landing somewhere else, okay? So that's what we call an accepted language of a graph, and we denote it by L sub gamma. L for the language, gamma is for the graph. So for example, if you have the following finite graph, my unique distinguished vertex is this O. The accepted language of this graph, well, what can you read? Well, you can read A, but you can also read A followed by B. You can read A followed by two B's. So the accepted language of this graph is A times B to the N, where N is a natural number or zero, right? Okay, I guess I should have had some arrow going in this direction. Okay, so let's see another example. Suppose you have the following graph, and let's again ask ourselves, what's the accepted language of this graph? Well, what can you read here? You can read A and all of its powers, right? You can do as many A's as you want. You can also do B and all of its powers, right? You can do B, you can do B squared, etc. You can also do some number of A's and follow them by some number of B's, right? So you can do, some number of A's and follow them by some number of B's. So the accepted language of this finite graph is going to actually look something like this. So you do some number of A's and you follow them by some number of B's. Okay, so let me now define what a regular language is. So let's start with a finite set, and let L be an infinite subset of the free monoid on A. Now, in general, L does not have to be infinite, but for all of my applications, L will be infinite. So I'm going to assume that I have an infinite subset of the free monoids. All that tells you is that you have an infinite collection of words. So we're going to say that this infinite collection of words is a regular language if it is the accepted language of some finite directed labeled graph. Okay? So let's very quickly see some examples. Suppose that we have the finite alphabet given by A, and I have the following language. Okay, so somebody has a question, right? Can you?
Yeah, I just have a quick question. You seem to only want to allow regular languages which are closed under ticking factors. Is that right? Because it's a standard definition, you would have accepting states, but because you're taking everybody accepted, you want like a factor closed language or something.
That's gonna come up in a second, right? I'm gonna read through the languages.
You're doing the language of a suffix shift, basically.
Yeah. So it's gonna come in.
Okay.
If it's not addressed yet, read through it. Okay, so
just a second, Abdul. I think we are having difficulties with your sound. At least I do.
Can you hear me better?
No, I mean you're breaking up, right? Is anybody else having the same problem that I do?
Yeah, he's breaking up. He's getting a weird feedback echo.
Yeah, there is something wrong with the sound, Abdul. Are you having an unstable internet connection, perhaps?
Well, I think. Let me see.
You were fine before, and then suddenly something happened.
I think that which was fine on the university. Okay, so maybe I'll try to log out and see what you have said. I don't know. Is it getting better or still problematic?
There is like a really bad feedback now. We basically can.
Okay, let me just leave and come back and see you. Okay.
Can you? One moment. I think he's going to probably try to rejoin us. So let's just stay online and see what happens, because I don't know what's going on, but something must have gone wrong. Unfortunately, this is
must have been my question.
Who was this? Yeah. So.
Okay. Yeah. So how is this? Is this
now it's better? Yes. I don't know. I don't know what happened. Sorry. Let's try again.
Yeah,
I mean, now you sound fine. You know. So let's try to resume from the point where you were. You know.
Okay. Very good. I apologize about that. Let's see. Okay, excellent. Is it still going well or not? I wonder.
It's fine now. Yeah.
Okay. Please let me know if it's not at any point, so I can try to do something. Anyway, okay. So we have the following. I have my alphabets, which is given by A, and let me actually also hide those which were hidden before. 1 second. Okay. So I have my alphabets, which is just the subset of one element A, and I have the following language, and I'm asking, is this language regular? Asking whether this language is regular or not means, can you come up with a finite directed labeled graph which reads precisely those? Well, we can, because we did this example before, right? You have a graph which has exactly one vertex, which is the unique distinguished vertex, and you just do as many as you want. Okay, very good. So let's look at the following example. Suppose your alphabet is AB, and you take the following language, and you ask yourself, is this language a regular language? I.e., can you come up with a finite directed labeled graph whose accepted words is precisely this? Well, yes, because we just did this example, right? The only difference now was that we were starting with the set, and we're looking for the graph. And the answer is yes, because we cheated, and we did this example. Okay, so now suppose you have a language which looks as follows. You have A to power N followed by B to power N. The main difference here is that the N's match, where in this example, they did not have to match. And I'm going to pose the same question. Is this a regular language? Is L a regular language? You could sit down and try to come up with a finite directed labeled graph, which will read precisely this, and you won't be able to. And it's natural to wonder, what is it that is so fundamentally different between these two examples that we just considered? So the first example is this one, and we saw that this is a regular language. And the second example is this one, and I'm claiming that it's not a regular language. There is actually, we can prove it's not a regular language, but you can sit down and try to come up with a finite directed labeled graph which would read this, and you won't be able to. So I'm claiming that this is not a regular language. Now, what is so fundamentally different between these two very similar looking languages that makes the first a regular one and the second not a regular one? Well, see, in the first example, the rules said, do any number of A's and follow them by any number of B's. You did not need to remember the number of A's you have done to do the B's. We just said, do any number of A's, do 100 A's, and then do 2 B's. That's fine. So you didn't need to keep track of how many A's you've done to do the B's. While in the second example, if you've done 100 A's, you must also do 100 B's. If you've done zillion A's, you must also do zillion B's, i.e. you must keep track of the... So the main difference between the two examples is that in the first example, you didn't need to have any memory. You might have, like in the first example, you needed only finite or even no memory, while in the second example, you need an infinite memory to be able to produce the language. Now let's make this slightly more precise. So suppose you have a regular language L over A. What does that tell you intuitively? How should we be thinking about regular languages? There are many ways to think about what they are, but the first one is what we just discussed. It's something that only has finite memory. In order to know what to do next, you only need to look at your most previous few steps, okay? So this is like again, you should keep looking at these two examples. In the first example, I didn't need to keep track of the A's, right? It's okay to keep track of the A's. The problem is I don't want to keep track of an infinite number of A's. That's what causes me problems, okay? So the first thing the first intuition of what the regular language is, it's something that only has finite memory. Okay, you can't keep track of infinite things. Okay, all right, so very good. Okay, so here is another point of view, which is very similar. Suppose you have a really long word W, and you know that so far W is in L, and you wish to know whether WA is in L or not. The question of whether WA is in L or not is determined by finitely many rules uniformly. You don't need to keep track of the entire W to know whether WA is in L or not. Okay? Whether W is long or short or very, very long, it doesn't matter. The question of whether WA is back in L or not does not depend on the length. Okay? It's only determined by uniformly finitely many rules. So this is one of the ways we think about regular languages. Those are just some pieces of intuition to have in mind. Okay, right. Okay, so this is what I just said. Okay, so now we're gonna revisit regular languages. Someone made a comment earlier, and I believe this is what they meant. So, okay, so we defined what a regular language is. We said that L is a regular language if it's the accepted language of some finite directed labeled graph. And I did lie, because the thing that I did not tell you is that not every vertex has to be an accept vertex. What I mean by that, it's okay to declare few vertices as reject vertices. To say that, okay, if I happen to start at my unique initial vertex and land at one of these 3 vertices, those won't be accepted words. I.e., you have a graph which contains some reject vertices. Containing reject vertices means that if you end there, you don't take that word in your language. Okay, so that's more precisely, that's what a regular language is. So for example, we saw that the language that looks as a to power m is a regular language, and this is a very, very similarly looking language. I have AB and I have AB to the m. So it would be weird if this language was not regular, because it's a copy of the previous language. It ought to be regular, and in fact it is. Okay, so here is a finite directed labeled graph. I have my unique initial vertex here. So let's see, what is this finite directed graph reading? You're reading A, you're reading AB, you're reading ABA, you're reading ABAB. So this is reading slightly more than I want, right? Because I only want to read powers of AB. For example, I should not be able to read A. I should not be able to read ABA. So what you do is you just declare this vertex as a reject vertex. If you declare this vertex as a reject vertex, you will do A, you say, okay, that's not accepted. And then you do B, that is accepted. So you have AB, and you just keep going and you get all powers of A, okay? Okay, so let me quickly remind you of what a geodesic is. If you have a metric space and you have 2 points, a geodesic is a path of a minimal length, okay? So you just look at the collection of all paths connecting X to Y, and a geodesic by definition is the closest such path. It doesn't have to be unique, so I shouldn't have said the, it's a closest such path. It doesn't even have to exist in a general metric space, but if it exists, we call it a geodesic. Okay, so let's consider the following 3 examples. My first example is R, and I would like to pose the question, what does it take not to be a geodesic in R? Well, the only way, so let's say that this point here is X, and this point here is Y. And if I take the path connecting them, that is a geodesic. That is the shortest way to go from X to Y. So it seems like everything in R is in fact a geodesic. However, there are things in R which are not geodesics. For example, if you start, let's say that you start at this X here. Okay, so maybe, let's see. Okay, so let's say that you start at this X here, and you go to this Y. Okay, so you are a geodesic so far. But if you backtrack a little bit, that is not a geodesic, right? So going to Y and backtracking for a bit is not a geodesic. And notice the failure of being a geodesic here happened locally. You could witness the failure of being a geodesic near Y. You didn't need to keep track of the entire. So for example, if you have a really, really long, so let's say that maybe here is X prime and Y prime is somewhere really, really far, right? So you go to Y prime, and then you backtrack. The failure of being a geodesic happened in your most very last bet. You didn't need to keep track of the entire length of the geodesic to see if you fail to be a geodesic or not. All I'm saying here is that being a geodesic in R is a local property. If it fails locally, okay? And it's a similar thing happens in a tree. Anytime you have a tree, you have the exact same behavior, right? If this is X, look like X, if this is X, and this is Y, and you go from X to Y, you are a geodesic. The only way to fail being a geodesic is to pause or to go back, and both of these can also be witnessed locally. However, if you have an infinite collection of circles, let's say that this is of length 1, this is of length 2, this is of length 3, failing being a geodesic here does not happen locally. Let's see why. Let's say that you have this really, really long circle here. Notice I'm a geodesic, I'm a geodesic, I'm a geodesic, I'm a geodesic, I'm a geodesic. As soon as I reach this point here and I pass it, I surpass it, I'm not a geodesic anymore because I have a shorter way of getting to that point. However, failing of being a geodesic here did not happen in this neighborhood. Neither did it happen in this neighborhood or this neighborhood. You actually needed to keep track of the entire thing to know if you're a geodesic or not. Okay, and this is a very fundamental difference between how geodesics are in positively curved spaces versus like negatively curved spaces. And you should already expect that this should have some reflection in regular languages, because regular languages have the exact same idea, right? To know whether WA is back in the language or not. Suppose that you know that L is a regular language, okay, and you know that W is an L. To know that whether WA is back in L or not, we said that you need only to check your most few steps. You don't need to check the entire history of W to know whether WA is an L or not. So it seems like there is some relation, and we'll see what we mean by this more precisely in a second. Okay, so suppose you have a finitely generated group, G. Let me just remind you what the Cayley graph of G is, or define it to you if you don't know what it is. So the Cayley graph is a graph. So if I tell you that something is a graph, I owe you 2 pieces of information. What are the vertices? What are the edges? So the vertices are simply group elements of G, and you connect 2 vertices with an edge if they differ by a generating element. So you connect G with H if G inverse H is an A. And the Cayley graph of G with respect to a finite generating set is going to be denoted by K of GA. Okay? Okay, so I'm going to define the growth function of a group, but what I will actually define is the spherical growth. But understanding the spherical growth and understanding the growth are very related. So I'm just going to call the spherical growth for the rest of the talk, okay? So the growth of a group G is defined as follows. For each integer n, you assign the number of group elements of exactly that length, okay? So let's see what I mean. Suppose you have the group of integers Z generated by A. I'm asking, so the question that I'm asking is the following. I'm asking, so let's see. So here is, right. So I'm asking the question. The question that I'm asking is, if I give you a certain n, let's say that you have, let's say that n is 5, how many elements of length 5 do you have here? You have exactly 2, right? How many elements of length 10 do you have? You have exactly 2. So the growth function of z, or the spherical growth function of z, is just 2. Notice that for the group z, the growth function is very simple. It's the constant function. It's as simple as it can get. At each, it does not vary, right? At each step, it's just 2. So the growth function here is quite simple. You just add 2 at each step. Okay, so let's do the following. So let's take the subset consisting of A, and by little a, I'm thinking of going in this direction, and by large A, I'm thinking of going in this direction. And let's take the free monoid over that, okay? So this is a collection of words. Let's take a sub-collection of words which consists of geodesic words. For example, so I'm going to define L to be the sub-collection which consists of all geodesic words, okay? So geodesic words tells me, for example, that this element here should not be an element in L, while this element should be an element in L, right? Now, notice that failure of being a geodesic in here also happens at the last step. What I mean is, if I hand you a really long word, and I ask you, is this a geodesic or not? All you really need to, so maybe, okay, so maybe I'll say something slightly more formal. So let's say that you know that W is a geodesic so far. So W is in the language. So W is a geodesic. And let's say that we ask, is WA a geodesic or not? The question of whether WA is a geodesic or not is determined by the very last letter of W. If the very last letter of W is not large A, then the answer is yes. Otherwise, the answer is no. Okay? So the point is, it seems like geodesics in Z should be a regular language, and in fact, they are. So geodesics in Z do form a regular language, and here is a finite directed labeled graph which reads precisely geodesics in Z. You start at O, and if you want geodesics going in this direction, you do A and all of its powers, and if you want geodesics going in this direction, you do large A and all of its powers. Now, notice that there is a relation between the fact that the growth function here was just the constant term 2, and between how simple the finite graph that reads geodesics here is. I.e., the fact that we have a regular language for geodesics here is precisely what made the fact that we have a finite graph reading geodesics here is precisely the reason why we had a very simple growth function. And I'll tell you what I mean by this more formally in a second. So I'm going to make the following definition. Suppose you have a sequence of spherical growths of some groups. So AN is the spherical growth of some group. We're going to say that AN has a simple or rational growth if the sequence AN satisfies a finite linear recursion. I.e., if I have a sequence of growths that looks something like AN equals 3 times AN minus 1 plus 2 times AN plus 1, I'm going to call this sequence a simple sequence by definition. My definition is telling me if my sequence satisfies a finite linear recursion, I'm going to call it simple or rational. Okay, so this is what I just said more formally. So okay. Now here is a combinatorial fact. If you have a sequence which satisfies a finite linear recursion, that's equivalent to its generating function being rational. I.e., if you know that a sequence AN satisfies a finite linear recursion, that's equivalent to saying that the sum of AN x to the n, where n goes from 0 up to infinity, looks like P of x over Q of x. So this justifies why we called such a sequence simple or rational. The sequence has a simple or rational growth. Okay. 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 Now let's just make the following observation. So we said the way we think about regular languages is in order to, if you know that W is an L, in order to tell whether WA is an L or not, you only need to know your most few recent letters of, you don't need to keep track of the entire W to determine whether WA is an L or not, okay? Now here there is a very similar idea. What this tells you to understand the nth term of your sequence, you need only to understand your most recent k steps, right? Satisfying a finite linear recursion means if you know the first k steps, you determine the rest of the sequence, right? The k plus 1th term is determined by this formula, and then the k plus 2th term is determined by, you know. Right, so I just wanted to point this out. So there is a relation between having a regular language and having a rational growth. In fact, anytime you have a regular language, or let's actually, all right, so, okay, so let's look at the Cayley graph of F2, okay? And let's again ask the question, what does it take not to be a geodesic here? Well, as you know, the Cayley graph of F2 is very similar to it of Z. The question of whether you are a geodesic or not is actually encoded in your most recent letter. For example, if I hand you a word W, and you know that W is a geodesic, so let's say that W is a geodesic, and we append a letter X and we ask, is WX a geodesic or not? To answer this question, you only need to know the last letter of W. If the last letter of W is capital X, it means no. If the last letter of W is anything else, it means yes. So you should expect the language of geodesics in F2 to be regular. Okay, and that this is actually the case. So the language of geodesics in F2 does in fact form a regular language. Okay. Okay, so what is the spherical growth of F2? So again, let's say that you are standing at some step here. Okay. So let's say that that's your nth step, and you want to go one step further. Well, at each step, if you want to go one step further, you're going to increase by 3, right? So here you're going to increase by 3, here you're going to increase by 3. So this tells you that the growth function, the new step, should be 3 times whatever the old step was. Okay? And again, this is a reflection of the regular language. So if you have a regular language of geodesics, then the growth function should be regular. And that's not surprising because regular languages tell you you only need to keep track of the most recent few steps, and so does rational growth. Rational growth, or having a finite linear recursion, said you only need to know the first few steps of the sequence to determine the rest of the sequence. So it's not surprising that they're related. Okay. Now let's look at the following graph. So we discussed earlier that being a geodesic in this example here is not a local property. And that will reflect itself in saying that, you know, so let's say that I have some, so maybe I have some A going here, and I have some A going here, and I have some A going here, and I have some B going in this direction, and I have some B going in this direction. So I have the following graph, and I would like to ask, actually, I don't want just one A here. So actually, you know what? Here is all I'm trying to say. Let's maybe now look at this. All I was trying to say is that if you have an infinite wedge of spheres, you don't expect the language of geodesics here to be regular, right? Because again, to know whether you're a geodesic or not here, you have to keep track of your, you have to keep track of the entire thing. Okay, so let me make the following definition. A geodesic ray, gamma, is said to be decontracting if every disjoint ball from gamma projects to a subset of diameter at most d once projected to gamma. So here is a picture. So we're going to call this geodesic decontracting if for any disjoint ball from gamma, you project it to gamma, you get a subset of diameter at most d. Whether the disjoint ball is small or large, so the size does not matter as long as your ball is disjoint from gamma and you project it to gamma, you should get something of diameter at most d. That's what the definition says. So here is maybe a slightly better picture. You take a small or large ball, as long as it's disjoint from gamma, it should project to a subset of diameter at most d. Now, that would, if you're thinking of something like R2, you won't see any such examples. In R2, every geodesic ray is not decontracting for any d, because clearly, if you take larger and larger balls in R2 and you project them, you're going to get larger and larger subsets, right? So R2 does not contain any infinite contracting geodesic ray. However, in F2, every single geodesic is zero contracting, i.e., if I look at this geodesic ray, and I take any disjoint ball from it, so maybe I'll take a ball starting here, right? So this is a ball of length 1. If you project it to gamma, you're going to get a subset of diameter 0. So every geodesic in this example is zero contracting, while in R2, there is no infinite geodesic that's decontracting for any d, because you can take larger and larger balls that gives you larger and larger projections. Now there are examples, so these are two extreme examples. In this one, there was no contracting geodesics. In this one, every geodesic is contracting. So there are things that are in between. If I take the group, which is z plus z star z, I have 3 generators, and I ask for 2 of them to commute. Asking for 2 of them to commute will give you a flat, and asking for the third one to not commute with either is going to give me some tree-like directions, because C does not commute with either A or B. Okay, so so my A and B are the directions that live in a flat, and my C is the direction that's going in a tree direction. If I take the geodesic alpha, which is A, this geodesic ray is staying in a flat forever, therefore it's not contracting. However, if I take the geodesic ray, which is doing C, this geodesic ray is going in a tree direction. And you could sit down and think about it. It is actually zero contracting. And if you take the geodesic ray, which looks like, AC, i.e., you spin in a flat one time, and then you go up. You spin in a flat one more time, and then you go up. This is going to be 1 contracting. The largest projection that you will have will come from the time that you spin in a flat, and that time is 1, okay? Similarly, if you spin 2 times in a flat and you go up, you spin 2 times in a flat, this is going to be 2 contracting. The largest projection that you will have will come from the largest time you spin in a flat, and that's 2, okay? Okay, and similarly, if you have this guy, this is going to be n contracting, right? Okay, and in this example, a geodesic ray is going to be decontracting if and only if you spin the most d time in a flat. Okay. Okay, so let's so you could think of the following as either a definition or a theorem, depending on where you come from. So let's say that you have G, which is a finitely generated group. So we're going to say that a group G is defined to be said to be hyperbolic if there exists a constant d such that every geodesic in the K graph is decontracting for that one uniform d. For example, in the free groups example, the free group is hyperbolic because, as we saw, every single geodesic in the free group is zero contracting. Okay, while in the tree of flats example, this example is not an example of a hyperbolic group because we saw, for example, that the geodesic A is not decontracting, right? Right. So this tells you that you could think of decontracting geodesics as hyperbolic-like directions. What do I mean? Those geodesics characterize being hyperbolic, i.e. you are hyperbolic if and only if you are decontracting for the same d. So this is a reason to say that decontracting geodesics describe hyperbolic directions. But you can also see them in other places, right? You can also see them in places like this. Therefore, when you see them in places like this, you think of them as hyperbolic-like directions. This is just a terminology, which is, yeah. Okay. Okay, so, right. So we discussed earlier that if you look at the free group on 2 letters, the language of geodesic words is a regular language. And you could ask yourself, is this a fact about free groups or it's a fact about hyperbolic groups? Because F2 was a hyperbolic group. And in fact, a theorem by Cannon in 1984 tells you that this is a fact about hyperbolic groups. So if you give me any hyperbolic group with any finite generating set, then the language of all geodesics forms a regular language. Okay? Okay, so there is a quote by Cannon that he mentions after he says this theorem, which I was planning to share with you, but I will skip. I think this quote is nice, but maybe we'll come back to it at the end of the talk. Okay, so I hope the following question is natural. Hyperbolic groups are described by ones where every single geodesic is decontracting with the same D. We saw that the language of geodesics in a hyperbolic group is a regular language. So you might wonder, is the regularity of the language a fact about hyperbolic group, or it's a fact about decontracting geodesics? I.e., if I have a finitely generated group, which is not hyperbolic, something like the tree of flats, and if I look at the collection of, if I only consider the collection of decontracting geodesics, will that by itself form a regular language or not? And the answer to this is actually yes. I.e., if you give me a finitely generated group, and you give me a finitely generated group, and you give me a finite generating set, and you fix a constant D, then the language that consists of decontracting geodesics is a regular language. Okay? And this is probably not very surprising, because if you remember in the tree of flats example, if you remember, let's say being 3 contracting. So let me actually quickly remind you of what that example was. So we had A, B, C, and we also knew that A and B commuted. So A and B gave me the flat direction, right? So we saw that if you spend like 3 times in a flat, and then you go up in the 3 direction, and then you spend another 3 times in a flat, and then you go up, you spend another 3 times in a flat, and you go up, etc. So we saw that this was 3 contracting, right? Now, what does it take not to be 3 contracting? In order to tell whether you're 3 contracting or not, you need only to keep track of your most recent 3 letters. If your most recent 3 letters are all in a flat, then the next one must leave the flat. And if your most recent 3 letters are not all in a flat, then you can stay for a bit longer. I.e., the question of whether you continue in a decontracting way or not is encoded in your most recent D steps. You just look at the last D steps. Are you in a flat? If the answer is yes for all of them, it means leave. Otherwise, it means stay for a bit longer. So this is why we expected this language to be a regular language, and in fact it is. This is a joint work with Ake. Okay, so this immediately tells you something cool. It tells you that, okay, decontracting geodesics are in fact hyperbolic-like directions in even a more meaningful way, because not only do they characterize hyperbolicity, but lots of the theorems some of the theorems that are true about hyperbolic groups, they carry over to decontracting geodesics in more general groups, okay? And a consequence of this theorem is the following. Torsion groups cannot contain any infinite contracting geodesics. And the reason for this is that this is actually easy to see. Suppose you have a torsion group which contains an infinite contracting geodesic. You take your infinite contracting geodesic and you run it by your finite graph. Because, so we know that so this theorem tells you that there exists a finite directed labeled graph which reads decontracting geodesics, okay? So you take your infinite contracting geodesic and you run it by your finite directed labeled graph. You must visit some vertex twice because your geodesic is infinite and your graph is finite. So pigeonhole tells you there must be one vertex which you visit twice. And then you just look at that loop that you read over that vertex and you iterate it over and over. And this should give you an infinite order isometry. It will give you an infinite order isometry because the labels of the loop are giving you a geodesic, RE, IE. The more and more you do them, the further and further away you get from the identity. So an immediate consequence of the existence of a regular language for decontracting geodesic is that they cannot exist in any torsion group, okay? Okay, so this tells you that, okay, decontracting geodesics are hyperbolic-like in even a more meaningful way because torsion groups and hyperbolicity are almost orthogonal to each other, right? So if decontracting geodesics existed in torsion groups, that would be weird. That would be like, how can you claim that they are hyperbolic-like, but you can see them in torsion groups, but you can't. Okay, so this is All right, so let's make the following definition. Suppose you have a geodesic metric space, okay? A geodesic is going to be called M Morse. So, okay, you have a geodesic metric space. I'm going to fix a function on two variables going from R plus to R plus. And a geodesic is going to be called M Morse if KC quasi-geodesics with endpoint on gamma stay MKC close to gamma. This is lots of words, but let me tell you what it actually means. So here is a geodesic. This geodesic is going to be called M Morse if quasi-geodesics based on it, okay, stay M close to it, where this M depends on how quasi you are. Of course, you should depend on how quasi you are, right? So that's what it means to be M Morse. M is a function on two variables. It tells you how, on two variables. These two variables tells you how quasi-geodesic you are. So I have this KC quasi-geodesic. And being M Morse tells me if you hand me a KC quasi-geodesic starting and ending at gamma, it must remain M of KC close to gamma. So you must remain close to gamma, where how close depends on how quasi you are. Okay? So let's see some examples. In F2, every single geodesic is M Morse, right? Because you can see. So here is some geodesic. It doesn't have to be infinite. Okay, so if you take some quasi-geodesic, the only way a quasi-geodesic can get far is if you backtrack, i.e., the only way a quasi-geodesic could escape the geodesic is if you make your quasi-constants bad. That's why the function M needs to depend on K and C. So the reason this was a bit far is because your K and C got worse. So you're allowed to get further and further from the geodesic, but that would be at the cost of increasing your quasi-geodesic constants. If your quasi-geodesic constants are fixed, if you fix your quasi-geodesic constants, you must stay uniformly close. Okay, so let's see a non-example. So let's take this infinite geodesic here. So here is a 3-0 quasi-geodesic. Here is also a 3-0 quasi-geodesic. Here is also a 3-0 quasi-geodesic. All of these quasi-geodesics are 3-0, i.e., all of them are quasi-geodesics with the same constant. Nonetheless, they get arbitrarily far from you. Okay? So in Z+Z, there exists no infinite Morse geodesic rays, while in F2, every geodesic ray is Morse. Similarly to the contracting property, if you take the example Z+Z star Z, you're going to see both types of behavior. If you stay in a flat forever, you're not going to be Morse, but then if you spend a uniform time in a flat, you are going to be Morse. So it's the two properties are related. In fact, here's one way they are related. If you take a geodesic, so suppose you have a proper geodesic metric space, and so this result is due to Harold-Schulten. If you have a proper geodesic metric space, and you know that a geodesic is contracting, then it must be Morse. So the contracting property is stronger than the Morse property. In fact, it's strictly stronger. So the converse is not true. It's not hard at all to come up. I mean, we can talk about this later, but it's not hard to come up with examples which are Morse, examples of geodesics which are Morse but not contracting. So the contracting property is in fact strictly weaker. Nonetheless, Morse geodesics do characterize hyperbolicity, i.e., a finitely generated group is hyperbolic if and only if there exists a uniform Morse gauge M such that every geodesic in the Cayley graph is M Morse. So this suggests that M Morse geodesics are also hyperbolic-like directions because they characterize hyperbolic groups and they also appear in other places like the tree of flats. Okay, so we're going to revisit this claim in a bit. So far, it seems reasonable, at least, to say that, okay, we're gonna think of those geodesics as hyperbolic-like directions. I hope the following question is natural. Given a finitely generated group and you fix a Morse gauge M, does the language of M Morse geodesics form a regular language? Both contracting geodesics and Morse geodesics we claimed are hyperbolic-like. Contracting geodesics had a regular language for decontracting the geodesics form the regular language.
Just a second.
Yes.
So I wanted to ask, so the standard Morse gauge for hyperbolic metric spaces, how does it depend on K and C? Is it like logarithmic in K and additive in C? Is that what it is? At some point, I remember I did this computation, but by now I forgot. Does anyone, do you remember?
So how does the Morse gauge, in a hyperbolic space, you're saying?
Yeah.
How does the...
What is it actually? The standard M.
Yeah, I don't know what it is. I don't know what, like, yeah, I don't know what it is. It seems like in the free group, it should be something like K times C is what I think. Like in the free group, I think it's.
I mean, the free group may be a special case, but I think that
right. Yeah, I'm not sure what the, yeah. So you're asking about the exact function. What is
I mean, okay. If you don't remember, don't remember. Never mind. Sorry. Go ahead.
Yeah. Right. Yeah. Okay. So let's see. So suppose that you have. I mean, you're right. So in hyperbolic groups, in the hyperbolic groups case, that's just the stability lemma. That's the stability lemma that we know, right? Which just says that quasi-geodesics stay close to geodesics. Anyway, so let's right. So let's say that you have a finitely generated group and you fix a Morse gauge M, and we want to ask, is the language of M Morse geodesics a regular language or not? Okay, and the answer to this question is no. So Olsen, Olshansky, and Sapir, they came up with an example which Fink later on used. So Fink used their example to come up with a torsion group which contains an infinite Morse geodesic. Having a torsion group containing an infinite Morse geodesic tells you that it's not possible to have a regular language for M Morse geodesics, because if you do have a regular language, you can do the pigeonhole argument and say that you have a contracted, that you have a Morse, that you have. You can see that you should have some infinite order isometry, and that's not the case. So okay, so let's see. So we made the claim that those Morse geodesics are hyperbolic-like because they characterize hyperbolicity. However, they do appear in weird spaces. You do have infinite Morse geodesics in torsion groups. This is problematic, and it's contradictory to the claim that Morse geodesics are hyperbolic-like. If we claim that something is hyperbolic-like, you should not see it in torsion groups. Again, because torsion groups and hyperbolic groups basically don't have anything in common. So three mathematicians, which is Jacob Russell and David E. Cipriano and Tran, they came together and they said, okay, this is problematic, and we would like to generalize things about M Morse geodesics, but we can't because of the existence of such weird examples here. So they suggested the following. So they suggested studying spaces where Morse quasi-geodesics satisfy a local to global property, i.e., so let's make the following definition. A geodesic metric space X is said to have the Morse local to global property if local Morse quasi-geodesics are global Morse quasi-geodesics. Now, this needs lots of unpacking, and I will do some of it, but let me just tell you what it means. It basically tells you the following. It tells you if you have a really long path, and you wish to know whether this long path is M Morse or not, it suffices to check there exists some L, which depends. So suppose that we're interested in the question of, is this really long path M Morse or it's not? To tell whether this really long path is M Morse or not, it suffices to check locally. There exists a uniform L where if you happen to be M Morse in paths of length L, then the global thing is also M Morse, okay? I would like to point out that this is saying two things. It's not saying one thing. So this is saying that look, if you happen to be a Morse quasi-geodesic at a local scale, then at a global scale, you're going to be 1, a quasi-geodesic, to a Morse quasi-geodesic. And those two are two different statements, right? Like it's not clear. For example, if you look at Z plus Z, in Z plus Z, you could take some really, really large squares, okay? And in this example, you are a geodesic at a local scale, right? So this is a geodesic, this is a geodesic, this is a geodesic, but the concatenation is not a geodesic. So all I'm saying is that the content of this definition, you have two different, this definition is saying two different things. It's saying that local Morse quasi-geodesics are one, global quasi-geodesics, two, Morse global quasi-geodesics. And again, the picture is this. You have a really long path, and to check whether you're M Morse or not, it suffices to check in some neighborhood L, where L depends only on the Morse gauge M. So for each Morse gauge M, there exists an L, where if you happen to be M Morse at subpaths of length L, then the whole thing must also be M Morse. Okay, so that's what it means to be. That's what it means to have the Morse local to global property. Now, let me give you a non-example, and then I will give you an example. So here is a non-example. So a non-example is something like this. Okay, so you have something that looks like this. So you see, so far, every single quasi-geodesic is staying close to you. Okay. However, there is this really long quasi-geodesic that you haven't seen yet, but you will only see once you get here. I.e., if you take all of these, if you take this path here, quasi-geodesic starting and ending at this path, stay close, okay? So quasi-geodesic starting and ending here, stay close. Similarly, quasi-geodesic starting and ending at this path, also stay close. Quasi-geodesic starting and ending at this path, also stay close. However, as long as you add this extra piece, you're going to see that there is this really long quasi-geodesic which does not stay close. So this is an example where the Morse local to global property fails, despite the fact that I was Morse at a local scale, I was not Morse at a global scale. And again, the reason for the failure of being Morse at a global scale is the existence of large loops. That's why I tried to emphasize why the existence of large loops, gives you all types of problems. It tells you the language is not regular, etc., etc. So one way to think about what this definition is telling you, it's telling you, if you have a really long geodesic and you know that small semicircles stay close to you, you know that locally semicircles stay close to you, then globally any semicircle should also stay. So i.e. such a picture does not exist. In other words, again, if you look locally and quasi-geodesics stay close locally, they must look globally. What this is doing in terms of the group, it's just eliminating, it's just saying that your group cannot contain some really large loops. Okay, so that's what this definition is. Okay, so what are examples? Examples are basically most groups that geometric group theorists care about. Okay, so what do I mean by that? I mean mapping class groups are all satisfy the Morse local to global property. Cat0 groups all satisfy the Morse local to global property. Any fundamental group of a closed 3 manifold also satisfies the Morse local to global property. Hierarchical hyperbolic groups, relatively hyperbolic groups, any group which comes with some hyperbolicity. Like with the mapping class group, you have the curve complex, and you can use that to show that you have the Morse local to global property. With for example, Cat0 cube complexes, you have the contacted graph. So those are the groups that has the property. Okay, so I hope you have the following natural question. Suppose you have a group, and suppose the K graph does have the Morse local to global property, and let M be a Morse gauge. Does the collection of M Morse geodesic words in the K graph form a regular language? And the answer to this is yes. Okay. More precisely, if you have a finitely generated Morse local to global group, and you fix a Morse gauge M, and you look at the collection of M Morse geodesics in the group, then that does form a regular language. Okay. Okay, so here's a very quick piece of philosophy. So contracting geodesics in a finitely generated group, they are hyperbolic-like directions, because not only did they characterize hyperbolicity, but many theorems that were true about hyperbolic groups turned out to actually be properties of decontracting geodesics, such as regularity of the language. However, Morse geodesics, in some way, they are hyperbolic-like, in some ways they're not, right? Because, for example, they do characterize hyperbolicity. However, you see them in torsion groups, okay? And Morse geodesics and Morse local to global groups or spaces, they are hyperbolic-like. They are hyperbolic-like in a much more meaningful way. So you should think about these Morse local to global spaces as very good hosts of Morse geodesics, okay? So they give you some global geometry in which Morse geodesics actually become, they become much easier. They give you some global geometry that helps you prove things about Morse geodesics. Okay, so let's remind everyone of the definition of a quasi-convex subgroup. So suppose that you have a hyperbolic group G, and you have a subgroup H of the hyperbolic group G. A subgroup H of G is said to be quasi-convex if there exists a constant K such that geodesics starting and ending at H stay uniformly close to you, okay? So quasi-convex means you take a geodesic that starts and ends at the subgroup, it must stay uniformly K close to it, all right? Okay, now let's make the following definition. Suppose you have a finitely generated group. I'm not requiring to be hyperbolic anymore. And suppose you have a subgroup H of it. Okay, so here is a subgroup H of some finitely generated group. We're going to say that this subgroup is stable if two conditions are satisfied. The first one is for any 2 points in the group, there exists a uniformly M Morse geodesic connecting them. And the second condition says this M Morse geodesic must stay uniformly close to the group. Again, being stable means, it means two things. It means for any two elements in the group, there must exist an M Morse geodesic connecting them where the M is uniform for all elements in the group. Not only there exists an M Morse geodesic, but this M Morse geodesic must stay uniformly close. Now notice that this definition of stable subgroups, it coincides with the definition of quasi-convex subgroups, because if you live in a hyperbolic group, then every geodesic is M Morse. So this geodesic that I require to stay close, it was already M Morse because every geodesic is M Morse. So we didn't, here I did not need to say that there needs to exist an M Morse geodesic because there already are by default, okay? Okay, so the following is a theorem by Gersten, Short, and Cannon, and it tells you the following. It tells you that suppose you have a, so the theorem is by Gersten and Short, but they used work of Cannon. Suppose you have a finitely generated hyperbolic. Suppose you have a hyperbolic group and you have a finite generating set. Then we have the following: a subgroup H of G is quasi-convex in the Cayley graph if and only if the collection of geodesic words which start at the identity end in H form a regular language, i.e., being quasi-convex is equivalent to saying that the collection of geodesic words starting at the identity and landing somewhere in H forms a regular language. Okay? Okay. I hope that I convinced you that anytime you have a regular language, the growth should be rational. So it's not, it's not surprising from one So what 2 tells you if you have a quasi-convex subgroup of a hyperbolic group, then the growth of H and G is rational. What do I mean by the growth of H and G? You look at the Cayley graph of G, you take a ball of radius n in the Cayley graph of G, and you count how many elements in H do you have. So if you look at that function would be a rational function. And that's just a reflection of the fact that you have a regular language. Okay, so more recently, Dahmani, Footer, and Wise, they used this machinery of Gersten, Short, and Cannon, along with some other machinery, to show the following. What they show is that if you are an infinite index quasi-convex subgroup of a hyperbolic group, then the growth rate of the subgroup is strictly smaller than the growth rate of the entire group. What do I mean by the growth rate of the subgroup? What I mean is, for example, if your growth is something like 3 to power n times 5, the growth rate is this 3. So all this is, all this is telling you is that quasi-convex or hyperbolic groups grow exponentially faster than their quasi-convex subgroups. Okay, so if this is the rate for H, the rate for G must be at least like 3.01 or something. It can't be 3. Okay, so I hope you have the following also natural question. Is the same true for Morse local to global groups? Okay, what do I mean? Suppose you have a Morse local to global group. Then we have the following. We saw that if you were a hyperbolic group, then being quasi-convex was equivalent to saying that the collection of geodesics starting and ending at the subgroup is regular. So we do have a generalization for that for stable subgroups, i.e., suppose you have a Morse local to global group, then to say that the subgroup H of G is stable is equivalent to saying that the collection of geodesic words in the calligraph representing elements of H is a regular language, all of whose elements are uniformly M Morse. Okay, so this is the description that you would expect. This is the right generalization. So you are stable if and only if the collection of geodesic words starting and ending is regular, all of whose elements are also M Morse. Okay, and I hope it's not surprising that this tells you that if you have a stable subgroup of a Morse local to global group, then the growth of this stable subgroup in the calligraph should be a rational function. Okay, and right, so similarly, so we saw earlier that if you were a quasi-convex subgroup of a hyperbolic group, based on the result of the Hemani Futterman-Wise, the growth of quasi-convex subgroups were strictly smaller. This still holds if you have a Morse local to global group, i.e., if you have an infinite index stable subgroup of a Morse local to global group, then the growth rate of H is strictly smaller than the growth rate of G. Okay, so I will share one more piece of philosophy and I will end here. So what is this piece of philosophy? So as we saw, stable subgroups, they generalize quasi-convex subgroups of hyperbolic groups, okay? So you should expect them to behave closely to quasi-convex subgroups of hyperbolic groups. However, there are certain things that, I remember when stable subgroups first came out, lots of people were trying to carry things from the context of quasi-convex subgroups or hyperbolic groups and do them for stable subgroups. But it was not an easy task because in hyperbolic groups, you do have not only you know that your subgroup is convex, but you also have an ambient geometry, which helps you prove things about the stable subgroup. Like when you prove something about a quasi-convex subgroup, your argument is not only about the subgroup. You often have to appeal to the global geometry of being embedded in a hyperbolic group. So stable subgroups behave like quasi-convex subgroups in hyperbolic groups, but in general, you lack the ambient geometry. However, if you study stable subgroups in Morse local to global groups, not only do you have the geometry of stable subgroups, but you also have some global geometry that helps you do things for stable subgroups. And I will end here. So thank you.
All right, thank you very much. Let's thank the speaker. Thank you. All right, so now, if there are any questions for Abdul, please, you can unmute yourself and ask them. Any questions, comments, anything for the speaker? So you're welcome now to raise them. So I actually had like a minor question, which I think regarding one of your very last theorems from the previous slide regarding the growth rate going down. Can you go back to the slide?
Sure. So,
you probably didn't completely.
Yeah.
I mean, I think probably some quantifiers are missing there, like in this theorem below. I don't quite know what you're supposed to say there. Do you want to assume that the subgroup is of infinite index, or what do you want?
Yeah, the subgroup is of infinite index. That's true.
That's what it is. Yes, I see. Okay, thank you.
And so this A is right. So the growth rate is independent of the finite generating. The growth rate in general is not independent of the finite generating set. However, this gap is independent. It's I'll actually sorry.
But this is a statement for subgroups of infinite index, right? With respect to the ambient generating set, right?
There, can you say again?
A generating set of G or H?
G, right? Yeah.
A is a generating set for G, for the ambient.
G, right? That's what I thought. Yes. Yeah. So you count the number of elements of H,
That's right. Yeah.
in the ball of radius r in G. Right?
That's right. That's right. That's right. That's right.
Yeah, and that's what goes down, right? Yeah.
That's right. That's right. That's right.
Okay,
Yeah, so,
that's what I thought, but I wanted to make sure. Thank you.
Yeah. So those stable subgroups, they agree with convex to compact subgroups of the mapping class groups. So this tells you that the growth rate of convex to compact subgroups of the mapping class group is strictly smaller than that of the entire mapping class group. Yeah.
I had a couple of other questions. So in terms of the classes of groups for which this local to global Morse property has been established, so I take it hasn't been established in full generality for things like acylindrically hyperbolic groups, right?
That's right. I think if one can show it for acylindrically hyperbolic groups, it would show it would prove lots of the open problems about acylindrically hyperbolic groups. For example, being a Morse local to global property is a QI invariant, okay? And it does imply the existence of the existence of a Morse geodesic implies the existence of a Morse element. For example, you can see that from the regular language, right?
Yeah.
So if you show that acylindrically hyperbolic groups have the Morse local to global property, it would imply that acylindrically hyperbolic groups cannot be QI to torsion groups. And that's not known yet. It's not known if, this is one of the weird things about acylindrical hyperbolic groups. It's not known whether they can be quasi-symmetric to even torsion groups.
And for out of n, it's also not known yet.
It's not also known for out of n. Yeah, there are some conjectures relating den function to Morse local to global groups.
Yeah. Okay, very good. All right. Sorry. Any other questions for anybody or any comments? All right, so then let's thank the speaker again. Thank you. So then I'll let me find. So sorry, can you stop the? Actually, probably I can find my recording button if I look hard enough. So let me stop the recording.